Okay, so good morning to everyone who's still awake and hasn't rolled back over to sleep. Going to be talking about MRI physics this morning. Um, MRI physics is kind of like we were just discussing, the section in physics that we seem to never get to each year. Um, we either run out of time or we can't find our physicist. And as a result, at least my year, I don't think we've ever gotten really much in the way of formal teaching about it. So, MRI is a literal bottomless pit of information, and you could spend weeks trying to learn it. I took the past week and went through these Einstein videos and tried to really get into it. But in the future, next year, you guys may not have the benefit of a global pandemic to buy you an extra 6 months of studying time for your boards. So my goal is going to be to kind of take from both Prometheus and War Machine and also these Einstein videos, which are really, really good, and try to make something that still captures all the information you're going to need, um, but do it in a more timely manner. So to start, we're going to be talking about MRI signal today and how we generate the MR signal. And before we start talking about MRI, we're just going to review a couple of really basic concepts. These are not unique to MRI by any means, right? Contrast and spatial resolution. Um, we deal with these regardless of the modality that we're using. But just to review, so up here we've got our image, and it's a matrix of 4 by 4 pixels. And this is an example of high contrast, and we have our lesion, and we can see it nice and easily, and there's uh, a high degree of difference between the signal that we're interested in, or our lesion, and the adjacent uh, tissue, if you will. And that's ultimately what contrast is. It's your ability to tell two things that are right next to each other apart. Um, so by comparison, over here we have same size image, still 4 pixels by 4 pixels. Our lesion is still in the same spot. It's still the same size, 1 by 1 pixel. But in this case, it's a lot more difficult to tell it apart from the rest of the tissue, right? You can kind of faintly make it out, but certainly not as easy as this case. So this is a case of low contrast, right? This is your RCC on a non-con exam. Now, if you were to give a contrast agent, right, then maybe it would look more like this. So that's contrast. Can you tell two things apart that are right next to each other? Spatial resolution is the other thing that we think about, and that is our ability to tell where something is, our ability to localize it, and how specific can we get. So let's look at our first example again. Same image, a matrix of 4 by 4 pixels. And if we took our image and we divided it into quadrants, um, you know, our lesion is in the upper, left quadrant. And then within that quadrant, we can say, oh, well, it's actually in the lower and medial part of that upper outer quadrant. We can get somewhat specific. No trouble telling the lesion apart from the surrounding tissue. On the other hand, over here, now our image is 2 pixels by 2 pixels. Okay, now we have in total 4 pixels compared to 16 here. All right, so our pixel density here is much less. Now, we still have good contrast between our lesion and the surrounding tissue, but all we can say with any certainty is that the lesion is in the upper left quadrant. We can't say anything about where it is within that quadrant. So this is an example of low spatial resolution, right? Our contrast is still good, but our ability to localize the signal that we're interested in space is more limited. And so contrast and spatial resolution, again, not unique to MRI, but when we start talking about the signal that we're going to generate and how we're going to acquire it, it's important things to just keep in mind because ultimately, for us to generate diagnostic images, we need to be able to generate sufficient signal that has sufficient contrast and spatial resolution. So another thing that's going to pop up in our discussion is going to be vectors. So everyone, I'm sure, knows what a vector is, but to review, so a vector has two properties, right? It has a magnitude that is the length essentially of the vector itself, and then it has direction. And that direction could be with respect to this xy axis and what angle is it making. But suffice it to say, a vector is some magnitude in some direction. And if we remember back to basic geometry or trig or algebra or whatever, remember that a vector, any vector, can be deconstructed into two perpendicular vectors, right? Into a x component and a y component. We might eventually refer to these as transverse and longitudinal components, but it's essentially the same idea, right? So if I just gave you, if I took this line away and I just gave you these two vectors, you should be able to generate our vector of interest just off of that. Okay. So that's vectors, very basic. Okay, so with MRI, MRI is going to deal mainly with these active or unbalanced nuclei. So what does that mean? So active nuclei are nuclei that have more protons than neutrons. Basically, they're nuclei that are unbalanced. Okay, and because they're unbalanced, they're a little off center. If you put them in the presence of a magnetic field, like this blue arrow, they will actually spin, which is something that we call precession. And we'll touch on that a little bit more in a second. On the other hand, there's a lot of balanced nuclei, nuclei that have the same number of protons and neutrons. And these are going to be, they're going to be balanced. They're going to be stable, and those aren't going to be active. If you put those in a magnetic field, they're not going to exhibit this spin. They're not going to spin like tops. They're not going to precess. Okay, so in MRI, the things that we're interested in are these active nuclei. Okay, we don't care about this. Now a little bit more about these nuclei. So all the nuclei behave like little bar magnets. Is that actually what's going on? No, everything's quantum with MRI physics. But for all practical purposes, our active nuclei behave like little bar magnets. And we can describe their little magnetic fields by a vector, like we just talked about. Okay, some magnitude in some direction. Okay, so the vector describes the magnetic field or the magnetic moment of these nuclei. And as we said, the active nuclei, if you put them in a magnetic field, are going to precess. They're going to spin like a little top around, the axis of that field. And it's this fundamental unbalance of the nucleus that causes it to spin. And that's really what's going to be of interest, as we'll see in a second. All right, this is the only equation that we're going to touch on today, and it's actually pretty basic. So you may have heard of this. It's the Larmer Equation. And what this is saying, I've got, the components defined over here. There's some frequency is equal to this constant, which doesn't really matter what it is, some number. It's called the gyromagnetic ratio, times the external field strength. Okay, so if we look at our example, we have our activated our active nucleus, right? Our hydrogen nucleus. Hydrogen nucleus is just a proton, so it's active. And we put it in this magnetic field. And so now it's precessing, right? Like a little top. Okay, so the speed at which it's spinning, like a little top, the speed at which it's, moving in a circle around the axis of that field, that is going to be our frequency of precession. Okay, that's this right here. And then the field strength is, pretty self-explanatory. So all the Larmer equation is saying is that the speed at which our active nuclei spin or precess is proportional to the strength of the field. So, hydrogen nuclei, protons in a 1.5 Tesla field, are going to spin at some certain frequency. You put those same protons in a 3 Tesla field, they're going to spin at a different and proportionally greater frequency. Okay, so this is just the basic concept that we have to keep in mind is field strength and frequency of precession, how fast it's spinning, these are proportional to one another. So again, one more time, here's our proton, our hydrogen nucleus. It's got a vector that we can deconstruct into, two individual vectors that are perpendicular to each other. And if we wanted to, we could refer to this as, the longitudinal component, because it's longer, and transverse component, okay, because it's perpendicular to the longitudinal. So we're not dealing with individual protons, right? We're dealing with samples, patients that have billions and trillions of these protons in them. So if we look at a sample of these guys just at rest, this could be a cup of water, or this could be you laying in bed pretending to listen to this lecture. All of the protons in your body are doing this. They are all pointing different directions. They're all at different points in their spin cycle. And so the net magnetization of that glass of water or of you is zero, right? Because it all averages out. All of these individual, tiny magnetic fields are going to average to zero. On the other hand, if we take that sample and we put it in an external magnetic field, which we'll call B naught right here. That's this big blue arrow. If we take our sample and we put it in some external field, what happens is all of the protons are going to assume one of two alignments. They're either going to line up parallel to the direction of that external magnetic field, or their magnetic fields are going to align in an anti-parallel direction. Okay, parallel but pointing the other way. And it turns out that if you take the entire sample, there is going to be a tiny, tiny, tiny excess of protons in the anti-parallel direction. So that if you sum the whole sample together, what you end up with is a tiny net magnetization or net magnetization vector in the opposite direction of your external magnetic field. So in our sample at rest, no net magnetization, everything averages out to 0. Put that same sample in an external field. Everything assumes one of these orientations. There will be a tiny majority that assume the antiparallel orientation. And the result of that when you average them together is that you get a tiny net magnetization vector. So let's look at the same sample, but kind of from the top now. Okay, so we talked about what's happening with, the longitudinal part, right? What's happening with the magnetic fields of these protons? How about their precession, their spin? So if we look at these protons now from the top, let's say, you'll notice that at rest, they're all pointing different directions, they're doing their own thing, everything averages out. You put them in this external field, and even though we've placed them in the external field, they're still all at different points along that circle, right? If we were to imagine that, this is a clock face, right? And this is 12 o'clock, it's 3 o'clock. This guy might be at 4 o'clock, right? Or 4:30. This guy's at, 1:30. Okay, this guy's at 10 o'clock. So they're all at different parts in their cycle, in their route. And the net result of that is any sort of transverse magnetization, which is the component of, if we look at this guy, remember we can break this guy down into two parts, right? Into a vertical part and then into a short horizontal part. And we can use those two parts to describe the field. So if we look at these guys, our small parts of these vectors, they're still pointing different ways. They're at different phases in their path, different points along that clock face, and they're going to sum to 0. Okay, so our net, or our net magnetization in the transverse plane, which is that smaller component, is going to be this, which is a dot, which is nothing, doesn't have any magnitude. There's no transverse magnetization at this point. Another way to visualize this is a phase diagram, which is this. So over here we have signal, how much signal we're getting. And on the x-axis, this is just over time. So let's go back to our example here, our proton. So as our proton spins around, it's precessing, right, along the axis of the external magnetic field, which is, I guess, coming, out of your screen, right, because we're looking top down. So if we zoom up here, if we had a receiver here, something that was measuring signal, every time this magnetic field comes back around, it's going to induce a current in this little receiver up here, and we're going to get some signal. Okay. So as it gets closer to the receiver, maybe we get more signal. Zoom out here. As it starts to move further away, we get less signal. As it moves 180 degrees away, okay, now we have signal in the opposite direction down here. And then we come back, towards 12 o'clock, and we get more signal again. Okay. So this is just another way of visualizing what's happening in this population. And you'll notice that I've shown that we have pretty equal distribution of protons at different points along that cycle. They're dephased, okay? And when they're dephased, there is no net magnetization in that transverse plane. Back to real world. So, as I've mentioned, we're mainly interested in protons. First of all, we're interested in active nuclei because those are going to be the ones that spin. And we'll talk about why that's important shortly. hydrogen nuclei, which are basically protons, are good candidates for MRI. There's going to be more protons, more hydrogen nuclei in the human body than any other of those potentially active nuclei. Okay, your body is, 70% water. There's protons in water, obviously. There's protons in fat. There's protons in the majority of biological tissue. So that's the main reason why we use hydrogen. So if I'm talking about protons, or I'm talking about spins, or I'm talking about, nuclei, assume that we're talking about hydrogen nuclei. Okay, so this is an MRI scanner, a very basic MR scanner. And got a little coordinate system up here just to orient ourselves. This is the tube that we put the patients in, right? This is the bore. It's basically a big cylinder. And around the outside of the cylinder are coils. And basically, we pump a whole lot of juice through these coils. The whole thing is being cooled by helium gas. And by doing that, by putting a bunch of juice through these coils at low temperatures, we are able to generate a resting magnetic field, baseline magnetic field, okay, B naught. This is your 1.5 Tesla. This is your 3 Tesla. This is your 5, 7, 9, 11, etc. And the more research experimental magnets. Okay. You'll notice that the magnetic field is oriented along the z-axis here, right? It goes from one side of the bore to the other, and this is always the case, okay? This does not change. This magnet is always on. This magnetic field is always on, unless you, hopefully not you, decide to quench the magnet, and then it goes off very fast, and then the hospital loses money. But for our purposes, this is always on, and it's always in this direction. It's always along the long axis of the MRI scanner. So we were just talking about, what happens with a sample of protons at rest, and then what happens if you put those protons in the presence of a external magnetic field, right? So here's our patient, and he's just chilling out in, zone 2. He's not in the magnet. So he's not going to have any net magnetization, right? Because all of his individual protons, his billions and trillions of protons, all their tiny little magnetic fields, both in, the long direction and in the short direction. If you were going to deconstruct each one of those little spins into, 2 vectors like we talked about, it's all going to sum to 0, right? It's all going to average to 0. That works. So what if we take our patient, slide him into the scanner. Okay. So now he's in the presence of our 1.5 Tesla field, right? He's in the presence of B naught. So what's going to happen to all of those nuclei? This is what's going to happen to all of those nuclei, right? All those protons, they're going to assume one of these 2 directions, and we're going to get this. So if we go back to our example, by sliding the patient into the tube, right, in the presence of this magnetic field, there's now some net magnetization going on in the patient, okay? So the question is, are we done? Can we measure signal now? Can we get to the whole point of, this MRI business? And the answer is no. And the reason is, if you try to measure this magnetic field, because it's in the same axis as our big, 1.5 or 3 Tesla magnetic field, it's just going to be drowned out. So what actually happens is, if when we slide this person in, for every 10,000 protons that align pointing this direction towards the head, there's 10,006 pointing towards the feet. So your net magnetization is something on the order of 6 out of 10,000. So very small. Okay. And in the presence of this, you're not going to detect that kind of a difference. Okay. So what if we had some net magnetization that was, instead of being in the same plane as our magnetic field, what if it was in the perpendicular plane? What if it was in the transverse plane, right? Kind of in this XY transverse axis. Could we measure signal then? If we had a receiver out here, on the edge of the tube, would we be able to detect this signal? Yes, actually. Yes, we would. And we'll get into kind of the specifics of that. So what would this look like? Remember before, this is kind of from the top down again. To do this, to generate some magnetization in the transverse field. Now remember that, our net magnetization, this is basically a reflection of here, where we have our proton and we have the long axis of its magnetization, and it's spinning, it's precessing, right, around the z-axis. It's precessing around the axis of our big net magnetic field, right? This is what all those protons are doing. They're just either facing this direction or they're facing this direction. Okay. So what we're talking about here is, what if instead of having some net magnetization in the z-axis, what if we had net magnetization in the xy axis? What would that look like? Well, basically what we're talking about is this component here. If I go back to this diagram, it's this. It's this small little component, this transverse component, that describes, basically, how off axis is this proton wobbling, So if we could figure out a way to do that, to look at that signal, we might be in business. And the way to do that is, if you remember, the reason why we don't have any signal in that transverse, in that shorter axis, is because all of these guys look like this in the external field. They're all pointing different ways. They're all at different points in their cycle. But if we had a way of making it so that they were all in the same place at the same time, they were all in phase, right? Like this. If we sum all of those together, now it's not going to be 0, it's not going to be a dot. We might actually have a component of transverse magnetization that we could generate, that we could use to, that would actually be our MRI signal, okay? Something that we could measure. Same idea, just on a phase diagram, right? So instead of being distributed all along that cycle, now we've essentially made it so that all of these guys are at the same place at the same time. And so they'd be grouped, and we would actually get measurable signal here, right? And then again, when that cycle repeats, and then again, etc. Okay. How do we get all of these guys in phase? So the way to look at this is energy levels. And this goes into quantum, and we're not going to get into quantum. But this is the way to look at it. So in order of increasing energy, think about these as energy states, right? Getting higher and higher energy states. Here's our patient at rest down here, right? He doesn't have any net magnetization going on. Everything sums to 0. Okay. This is our patient in zone 2, just hanging out. The next higher energy state is this, where we have placed our patient into the magnet and generated some longitudinal magnetization, right? A net magnetization vector in the axis of B naught. This. That's the next level up. If we were to continue to put energy into the system, what's going to happen is that net magnetization in that long axis is actually going to get smaller. And as it gets smaller, two things are going to happen. One is that we're going to have growth of the magnetization, the net magnetization in the transverse plane, and decrease in the longitudinal plane. The other thing that's going to happen is all these guys viewed from the top, right? Here, they're all out of phase. They're all pointing in different directions. They're at different points along that phase diagram. As we add energy to the system, what happens is they're all going to get closer together to the point where they're all in phase. Okay? They're all at the same point in their phase cycle. Okay? So this is with increasing amounts of energy. Think about these as energy states, okay? And to get to the next energy state, to get to this is our goal, right? This is where we have our protons are all in phase, and because they're in phase, we generate, some magnetization that is out of the plane of our big strong magnet. And this is what we can measure. So how do we get from here, or from this? We showed how we got to here. How do we get to up here? The answer seems to be more energy, right? Okay, well, so what do we mean by more energy, right? There's different ways to add energy to a system. One way that we could add more energy to the system is just put them in a stronger magnet, a stronger external magnetic field. So here, I'm just illustrating the difference between a 1.5 Tesla magnet and a 3. And you'll notice that a 1.5 Tesla magnet, we generate some net magnetization vector. And a 3 Tesla magnet, that vector is bigger. Okay. This goes back to our example. As this field gets stronger, this external magnetic field, you're going to have a greater proportion, so more than that 6 out of 10,000, a greater proportion of protons in the anti-parallel direction compared to parallel. Okay. Now, it's still not enough to generate, magnetization that you would be able to detect in this plane, because this is still way, 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 way stronger. But it's more than you would have at a smaller magnetic field. That becomes relevant because what you're basically doing by increasing the strength of this field, going from 1.5 to 3 Tesla, is you're giving yourself more potential signal to work with, right? This vector is bigger than this vector. And this will become relevant later when we talk about, how we image things. But one of the takeaways here is that with a 3 Tesla magnet, you have more signal than with a 1.5 Tesla. Okay. But this is not how we get to our goal, which is transverse magnetization. basically, if we just kept increasing the strength of the magnetic field, we would kill the patient or cook them long before we got to the point where we had transverse magnetization. So just increasing the external field is not the way to go. Okay, so instead of making this field, our B naught, stronger, what if we applied another magnetic field in a perpendicular direction, like this, B1? Would that be enough to get this guy into the transverse plane? Kind of. Almost. Okay. What's going to happen if you do this is nothing. Okay. You're still going to be left, you're going to be stuck at this step. And the reason is that if you just apply a magnetic field, even though it's in some other direction than our resting magnetic field, if you just apply this field in a perpendicular direction, you're just going to do the same thing. You're just going to heat the patient up. And the reason is that, for reasons we'll talk about in a second, you're not getting efficient energy transfer from this magnetic field. Okay. You would still have to basically cook the patient alive for this field to ever put enough energy into the system to get to this. Okay. So the last piece of the puzzle is this idea of resonance. Okay. So we talked about, magnets, right? Our protons are hydrogen nuclei, which are the things that we're interested in with MRI. This is the resonance part of MRI. And the idea is that, these are supposed to be tuning forks, which is a thing that maybe you would use if you were still doing family medicine as a third-year medical student. And these tuning forks, you can get tuning forks that have different frequencies, right? When you bought your tuning fork for medical school, you had options of different frequencies, right? So the point here is resonance allows efficient energy transfer between similar frequencies. Okay. If you have two, we'll call them C tuning forks, they have the same frequency. If you hit this tuning fork with a patient's head, it's going to start to vibrate at some frequency. And if you take that and you put it next to another C tuning fork with the same resonant frequency, then it's going to start to vibrate. Okay? There's efficient transfer of that energy because they both have the same resonance. They both are resonating or have the ability to resonate at the same frequency. If you do the same thing and you put, you hit the patient's head with the C tuning fork, and then you put that tuning fork next to an E tuning fork, you're going to get minimal, if any, corresponding vibration of that E tuning fork. And the reason is that these are different frequencies. They will resonate at different frequencies. Okay. This is why this whole thing works. It's this idea of resonance. And again, resonance is the concept that you can efficiently transfer energy between things of similar frequencies. So, if we go back to our patient, what if instead of having a static field like this applied in the perpendicular in the transverse direction, what we actually do instead is we apply that field, but then that field alternates directions, this way, then it flips to this side. So people say, it spins, or it alternates, or it oscillates, whatever. But this changes directions. And the speed at which it changes directions is something that we can manipulate. And so it turns out that if we apply a magnetic field over here that's perpendicular to our 1.5 Tesla, if we apply a perpendicular magnetic field and we change its direction, we oscillate it at some frequency. Well, if that frequency is the same as the frequency of water protons or hydrogen nuclei in this magnetic field, because this is something we can calculate. We know the strength of the field. We know, here's our Larmer equation. We know the strength of the field. This is just some constant. You can look that up. We can figure out what the frequency of water or what the frequency of, the hydrogen nucleus is going to be. So we know what all those frequencies are in this patient, or what they should be. So if we set our field, our external field over here, to flip back and forth at that same frequency, what's going to happen? Because we're applying this field and we're applying it with some frequency that is equal to the frequency of the things that we care about in the patient, this situation allows for efficient energy transfer between this field and the patient, such that we're actually able to get up to this point. Okay, it's the principle of resonance that allows that. So just kind of putting it all together, this is everything that we've just talked about. This is our external magnetic field, 1.5 Tesla. This is our bore with the patient in it. We've been calling this, our NMV, right? Our net magnetization vector. From here on out, we're going to call it, just m sub z because it's in the z-axis. This is just the longitudinal part of the magnetization. Okay, it's the same thing. And this is our transverse magnetization, or m sub t. This is what we've just generated because of the efficient transfer of energy between this rotating perpendicular magnetic field and the patient. This rotating perpendicular magnetic field is something called the RF pulse, which is something that you may or may not have heard of before. But basically, the RF pulse is something that we're going to be talking about a lot. And this is how when that RF pulse is turned on, this is what allows us to generate magnetization in this transverse plane, out of plane of the external field. And this is the signal ultimately that we're going to be able to measure. So, the next part, if there is a next part, if you guys want me to do more of this, we'll talk about, now we figured out how to generate some signal. How does that actually translate into, T1, T2, T2 star, the things that we think about with these MRI images, all the different types of sequences, and then eventually artifacts. So hopefully that was helpful. This was about 45 minutes, and we covered basically the first 7 lectures worth of that MRI series. So, yeah, hopefully that was helpful. Let me know if you want me to do more, and we'll go from there.